Hey guys, today we're doing solving systems of linear equations graphically. We're going to be looking at two linear equations at the same time and essentially asking where do these graphs intersect? Because when the graphs intersect, you have the same x and y, and that is a solution for that graph that works for actually both of the graphs we're talking about. You'll see what I'm talking about soon. We're going to look at Max. Max challenges his brother, Eero, to a race on the way to football practice. He gives Eero a 20-yard head start. If Max runs 6 yards per second and Eero runs 4 yards per second, how long will it take Max to catch up to Eero? Now, I made these two equations where Max equals y equals 6x. That's his speed. Every second he's running 6 yards. He's quite a bit faster than Eero. Eero, however, he runs 4x plus 20. I gave him that plus 20 because that represents that 20 yards head start. Now I made y equaling the distance traveled, and x, of course, being the rate that that boy is traveling. Now, yeah, these are two different equations, but there will be a point. There will be a point when Eero and Max are right next to each other, right? There will be a point where Max inevitably passes Eero, and by finding a solution of the system of equations, we find when that moment will be. So if you graph both equations, the intersection is the solution, or that moment that he's passing. So when both y and x are solutions for both of them. Now, as you guys know, there's like an infinite number of solutions initially, independently. For x, I could say, for Max, if we're looking at Max's, I could say, at 10 seconds, he's ran 60, oh goodness, yards or meters? Yards. So at 10 seconds, he's run 60. At 10 seconds, he's run 50. Oh my goodness, I just happened upon the solution. At 10 seconds, he ran 60 as well. That totally was not on purpose. I found the solution. Oops. Oops. So, a better solution, or a better thing would be at 5 seconds, he's ran 40, and at 5 seconds over here, he's only ran 30. So he's not caught up to him yet. So we have two different things. And if you think about these as ordered pairs, over here we have 5:30, and over here we have 5:40. So even though it's the same x, we get different y's. So we're looking for when the x's and y's will be the same. And this graph shows you it. I graphed both of them by using the rise over run. This is a little skewed, all that jazz, but just trust me, it's all right. The rise over run, so there's a 6 over 1, where the bottom is representing the time and the side is representing the distance. As you can see, this is our intersecting point. That is when the solution works, which is, as I happened upon earlier, 1060. When x equals 10 for Eero and Max, they both have gone 60 yards. That is a real life application to what we're solving for and what we're doing today. Yeah, probably one of the more exciting real life applications, one of the more interesting ones that we've run into. You will only get better ones as we move along. Now, when we solve systems by graphing, to tell you the truth, this is not the most efficiently quick, fastest way to do it, but it works. So we're solving the system by graphing. The first thing we need to do is, if we can, get it into y equals mx plus b. Now this first one, of course, we can get it into y equals mx plus b, because we have a y and an x. 2y equals negative 5x plus 6, divide both sides by 2. I don't have enough room, so I'm just going to do all that in my head. Now the other one, there's no option to do it in y equals mx plus b because x equals 2. There's no y. X equals 2 is this line. So this line is x equals 2. The other one, we have a y-intercept of 3, and then 5 down, 1, 2, 3, 4, 5, and 2 over. Means we get something that looks like, oh my goodness. Oh, so now, I know that we talked about, well, does it matter how exact my graphs are? And for once, it actually does. We're actually going to start worrying about how exact our graphs are because we're looking for intersections. We're looking for when those graphs touch. And if your graphs are rather messy, well, you're going to be having a hard time finding that. Now, our final solution here is 2, -2. That's when you will get the same answer for both of these. Once again, we get into y equals mx plus b. The first one's rather easy. Y equals -x plus 4. The second one's already there. Hooray! The slope is obviously -1. For both of them, and one intercepts at this point, the other one intercepts at +4. So we go up here, and once again, our slopes are important. So I'm going to take the time to use my line thingamabob because that's the only way we're really going to figure out where they intersect. Oh no, they never do because they're parallel, and by their very definition they don't. Now notice that these lines both have the same slope. When lines have the same slope, they are parallel. When they are parallel, they never intersect by the very definition. So there are no intersections. There is no solution. You will never be able to put in an x and get and y and have both problems work. Now there are some terms that I'm going to be talking about. First off is a consistent equation. If a consistent equation is having at least one solution. Now that's very similar to our very first one, boop boop, where there is an intersection, we can point to it. An inconsistent therefore has no solution, and that is our parallel lines. Next is independent. Independent has two different lines that intersect. Again, very similar to our very first one. Whereas dependent is the exact same line. So as you guys know, sometimes you can rearrange equations and they look very different, but it's the same equation. I mean, that's what we were doing last time with standard and y equals mx plus b and point slope form. So in order to really know these, we have to get them both in y equals mx plus b. Now here's a lot of information. It's in your book as well. But I put this up here because, yeah, I want to talk about it. First off, we have the graph. Now, we have parallel lines, we have intersecting lines, which obviously is this, and we have the same line. Now, if we have parallel lines, the number of solutions, well, there's simply none. There are none. And if you're going to describe it, you'd say it's inconsistent. If you have intersecting lines, you have exactly one solution. There isn't more than one, there isn't less than one. There's exactly one, and it's consistent and it's independent. Again, vocab words. You are going to want to have those in your bookmark because you're going to need them for your homework. And then finally, if it's the exact same line, every single point on that line is a solution because it will work for both solutions. That means there are infinitely many solutions, and it's consistent and dependent. Okay, guys, we're doing every fourth today, a little weird, and then we're going to pick two of those. Oh, it should be 36, not 26. Pick two of those 36 to 42. Just pick the two that you feel like you can figure out the easiest. Good luck with those. And yeah, don't forget, I mean, the main thing that, again, the main two steps, get it into y equals mx plus b, and then look at those slopes, graph it out, see what it looks like, and sometimes you'll have to go the other way as well, but I believe in you guys. Have a good time doing some mathematics.